today's talk, the topics I want to, based on our term projects, so I want to deliver more information, more knowledge about the approximate nearest neighbor search. So the current state of the art is the graph-based search. So I want to use this tutorial slides given in CVPR 2023. So it's, although it's 2 years ago, but the advance in approximate nearest neighbor search is not too much, I have to say. Now, it's basically use the graph-based technique to do the approximate nearest neighbor search, especially for million scale, even billion scales. So I give an introduction for this. And the author of the slides from is Professor Matsui, so it's from the University of Tokyo. So the slides is very easy to understand, so I take these slides for you. And I also put the slides on my course website, so you can also download the slides from here, or you can find it from Google to download it. Okay, so it's Matsui. Professor Matsui is a very young scholar in University of Tokyo. So here is some his publication. And the outline of the slides is as follows. So I will give a background first, and it's the concept of the graph-based search. Okay, so it's including some basic operation like the construction for the graph, and also how to search, navigate in a graph. And we will also give some observation on it and its property. Some representative words in graph-based search, including HNSW, MSG, Lamana, and finally give some discussion for it. Okay, so first is the background. Let's review the basic idea of nearest neighbor search. Okay, so given a database, it's actually a vector database. So it's like our term projects. We have a bunch of vectors stored in the database. And this database contains n vectors. And each vector is a d-dimensional vector. Okay, so given the such a vector database, our goal is when the user submits a query Q, the Q is with us in the same dimensions. Okay, so there's a 4-dimensional vector. Okay, then we use this query Q to search in this vector database. Okay, and then there is you can say it's a ranking function. The ranking function is to evaluate the distance. We use the Euclidean distance to find which distance is smallest. So here the algorithm will return top n smallest distance vectors back to the user. Okay, so here is the result. Okay, we return the top one, the nearest neighbors to the user is the x74. The ID is 74. We can return it to the user. And for the ranking function, some method may use the inner product. So it means we will calculate inner product between the Q and the vector in the database. And here we will return the up max. So because the inner product is act like a similarity, so we will return the high score. It means the similarity is high, so we return it to the user. Okay, so it's the general idea by using a nearest neighbor search. Okay, but this method is very time consuming. So as you know, if we perform linear scale for each Q and as n in your database. So the linear scan time complexity is about n times d. So n is the number of vectors, and d is the dimensions. Okay, when n is scales to a very large, like a billion scale, so it will be a very time-consuming process to do the search. So that's why we need the approximate nearest neighbor search, of course, the ANN search. So the process is almost the same. Okay, so we give a query and search in our database and to try to find the minimum distance. But here, not with in the ranking function, we will have a preprocess. We build an index structure. The index structure helps us to filter out unnecessary matching between your vector and the query. So we can, with this, we can reduce a lot of computation. We don't need to compute all the data in the database. We use some database, some index structure like a tree or inverted files or the graph. Today we will talk about the graph-based structure. Okay, so with this, with the index structure, so we can have a faster search. And but the faster search is the price. The price is the accuracy will be decreased. But maybe just sacrifice a little bit accuracy, but you can accelerate your performance, your speed a lot. Okay, so it's a trade-off between your runtime and accuracy. And also because you build another, index structure. So the index structure will take another memory consumption for it. So you use tree or use the inverted file or use graph, they will consume a different scale of your memory. So we will talk about this later. Okay, so in this slide, we assume that your number of data is smaller than 10 to the 10 to the 9. It's less than billion scale. Okay, and so that all the data can be loaded in your memory. But if your data is more than billions, so it's difficult to load all your data in your memory in a personal computer. So in this situation, we will consider another method, but we will not mention in this slide. Okay, so there are some real-world use cases. So the first one is like a multimodal search. So multimodal search means we can use different modalities to do the search. For example, you can input your text query, but to search the image, or you input an image to search music. Okay, like this. Okay, so because your input and output are at different modalities, so this is called a multimodal or cross-modal search. Okay, so in this example, we show that given an image here. Okay, the first image. Okay, the second image, and many images. All these images you can throw the encoder. For example, like the clip image encoder, or like the vision transformer (VIT). Okay, search this. There's many such encoders. Okay, so we can use the encoder to encode these images into a vector. Okay, so they use the encoder that we embed that into a vector space. Okay, then here, suppose a user gives a query. It's a text query and two dogs playing in the snow. Okay, it's the text. Okay, so it's in different modalities. So you can imagine that the text representation is very different from the image representation. They are very different. But through some deep learning or some such as representation learning, we try to align the two different representation space can be aligned together. This is the basic idea in multimodal, in cross-modal research. Okay, so here we use the clip text. In clip model is already aligned the text representation and the image representation. Okay, so we can use this is the pre-trained model. Okay, use the clip text encoder. Okay, to maybe with some fine-tuning. Okay, you can transform the text into a vector too, with the same dimensions. Okay, so also a four-dimensional vector length search in your image database. So remember, in CLIP, based on these two pre-trained models, they are already the text and the image spaces they are already aligned. Okay, so they can search in the same space, and their measures we consider they are meaningful. Okay, so we then apply the same process to do the ranking. And with the ranking, we find the result here, and this is the image we find corresponding to the user's test query. Okay, so it's multi-modal search. So any problems? Here you can see the encoder we use the clip. Okay, you can use others, and the encoder usually determine your upper bound of your performance, the accuracy of your performance system, your system. And the ANN process is just like here. Okay, so you just use it, and so in such a multimodal search, you have to consider to integrate two different parts. One is your encoder, and the second part is your ANN search. So if you want to be accurate, you should try to maybe fine-tune these two models, the encoders. And if you want to be your search to be efficient, so you have to select a good ANN search algorithm. This slides can be found on my website. Okay, so if you want to download it, you just find this on this CVPR ANN search slides. The second use case is LLM. Use it in LLM. Okay, so there's the example. Suppose a user issue questions that who won the curling gold at the 2022 Winter Olympics. Okay, but he asked this question to the ChatGPT, which is trained in 2021. So basically, the ChatGPT doesn't have the knowledge before the 2021, but the user asked the question about the 2022. Okay, what will happen? So ChatGPT say, "I'm sorry, I don't have the knowledge for the future events." But if we use some technique like the RAG, retrieval augmented generative retrieval augmented generation, if we use such a technique, it can be done by this. Okay, we collect the more data, the future events from some website, such as Wikipedia. So in Wikipedia, we can find several such documents and talking about some events occurred in 2022, also including the Winter Olympics events. And so we just collect this all these documents, okay, we use a text encoder to transform them into a vector and store in our database. So again, is we generate the vector database. And for the text, for the user query, we store the same text encoder to transfer it into the same vectors, and then we apply the ANNS search again. And with this search, we output the result. We can output the top K document, and use this document. This document is closest to the user query. It's the list of the 2022 Winter Olympics medal winners. Okay. So we can feed this document to the Chih-GPT again. So it's the same query, but we have additional parts like use the below articles that we find from search process. Okay, so we can paste this information as a prompt and together with the Chih-GPT. So now the Chih-GPT has additional knowledge about 2022. So he can answer the query. Okay, so we call this basically the technical rate. Any comment? So from this you can find that, okay, so approximate news neighbor search can help to improve your language model's power. And actually maybe it's the easiest way to provide additional knowledge to language model. You don't need to retrain, to fine-tune the language model, because for our we cannot train it actually, even fine-tune it. Okay, it's a very big computation resources to be consumed. So this is the basic way, the easiest way to provide additional knowledge. Okay, for LLM. Okay, so here is we treat this vector DB. So you can as the developer of a search with the deep representation learning and also the language model. So it's like getting material required for a good performance for the vector DB is heavy. Okay, so now the ANNS search we already can divide it into three basic technologies, three levels. We can regard it from three different levels, from the algorithm, library, or service. In the algorithm, it's mainly addressed in some scientific papers, and also with our main research goals, research topics. There are some famous algorithms, so including the product combination, IBF. Okay, I have addressed in next 2 weeks. And today we will talk about the ANNS stuff. Okay, it's also very famous, published in PEN in 2019. And so another is advanced PQ. It's used 4-bit PQ. It's trying to design based on the hardware design, which is only 4 bits. Okay, so this we use also use the scan. Okay, so it's algorithm to further improve the performance of PQ. And for the ANNS search library, okay, this library actually implemented several algorithms. These algorithms including the PQ, HNSW, or scan. And this library usually implemented by some researchers or by companies. For example, like face is implemented by Meta, and others ANNS line or HMSW line or scale are implemented by some researchers. On the next level is the service. The service is at the database level. So in database level is also including several libraries. Okay, so maybe like here you can see there are several such a service, and each service may contain several libraries. Okay, they usually implemented by some companies. So because it's a service, they may charge you. Okay, so you can try to use some such a service to facilitate your construction for vector database. Okay, so here it say maybe one library may implement multiple algorithms, like face, it implemented PQ and IBF PQ, and also HXW. And one algorithm may be implemented by several multiple libraries. Okay, and also one service may use some library, so such as Milvus. Milvus is this service implement, including the face and HNSW line. And this is another service called Alleviate. Okay, it's we implement the HNSW use this library and in their service. Okay, so this slide will focus on algorithms. In this slide, I just show you at the different scale of your vector database. So the 10 to the 6 is like the median scale, and 10 to the 9 and 2 is the billion scale. But this talk, in this slide, will focus on the median scale. So in median scale, you can see we generally have two approaches. The left-hand approach is focused on we just process the raw data. We don't compress your vector data. Okay, so if you process on raw data, your accuracy, because you don't apply the compression, also your accuracy will be higher, but the memory consumption is also higher because the data is not compressed. Such a technique including like the LSH, locality certification. I will address this topic in next semester. Or use the tree partitions or graph. And on the right hand side is we will use some compressed technique like PQ, or some hash to do the compression. So if the data is compressed, the accuracy will be decreased, but your memory, you also decrease your memory usage. Such a technique including like the lookup base, use like the PQ, so you do the clustering and convert it into a cluster ID. Okay, so it's then you can use some lookup table to facilitate such a search. Okay, so this we can apply the PQ here, and then apply the symmetric distance to compute the distance between your query and then your compressed data. And also you can compress your vector into a binary code like this. So if we call them, at least we will compute their having distance between the two binary codes. So it's we compute the having distance and then do the linear scale. Okay, so for this part is data is compressed. Okay, so it's basically two approaches applied in the median scale. But when you extend your database to the billion scale, okay, so because if we want to load all your data, including your load, including your raw data or index structure. If you all of them want to load in your memory, okay, so this means the raw data cannot all fit in your memory. You have to apply the compression on it. So that's why in the billion scale, actually we need advanced technique. For example, like space partition to do the clustering or to do PQ and to reduce your data index structure. And also, you have to apply the data compression to compress the raw data, to apply some consolidation, and so on. So today we will focus on how to apply the graph traversal on it. Okay, so focus on median scale. And for billion scale, you will be next topic. Okay. Now let's start to introduce the graph-based search about its basic idea. Okay, so the graph-based search now is you can treat it as the standard of the state of the art. And if your data can be overloaded in your memory, so it will be very fast, and the accuracy is also is much higher than the conventional methods. So it's fast and accurate for real-world data. And also, because it consumes a lot of memory, so it's difficult to be scaled up to the billion scale. But now some method already developed to try to use some hardware, use SSD, or use some clustering technique, or use a hierarchical clustering, try to load the data from the for the billion scale data to your memory. So select graph search is still fundamental, can be applied in billion scale database. Okay, so in graph-based search, there are several key points. So here you see, suppose we build this graph. In this graph, you will have you use the node to represent the vector, and use the edge to connect two vectors. This means they are neighbors. So you will see such a graph structure. And in this graph structure, give a query, then we will try to use some algorithm, we call it a traversal algorithm, to visit this graph. And finally, we want to find the nearest node closest to your query. So it's our main idea. So you can see, you can regard it like a mass. And this is your entry point here. And then the query is your treasure. So the goal is quickly find the treasure and accurately locate the nearest point to the query. So you see there is a path from your entry point and through the path to finally find the nearest node, the nearest neighbor to the query. So the tutorial, we try to make the graph search not a black box. So let's first consider how to construct such a graph structure. Here we see there are two different approaches. The first is incremental approach, and the second is the refinement approach. So in incremental approach, basically we will, if we will add a new item, a new vector, one by one. Each time when you add a new vector here, then you will find its nearest neighbors and then build the connection, the edges between them. So it's called an incremental approach. Okay, so this suppose here in this graph we already have 90 nodes and build the graph for the 90 vectors. And here each node is a vector, and if they are neighbors, we will build an edge between them. But you find that some edges are very long. You see, from the node to this node, the edge is extremely long. You see, some nodes have a very long edge to connect to a long distance node. So we would call such edge is a shortcut. The shortcut is try to speed up the search process. So sometimes it means sometimes you don't need. You can connect some long distance node with an edge. You can jump to this area quickly. Okay, we will talk it later. Okay, now we have given a new vector. It's an x91. It's a new vector here. Okay, so the next step is we try to build up this edge. Find its nearest neighbors first. Okay, so we can use the search algorithm. For example, you can just use the ANNS, the search algorithm, to find its nearest neighbors according to the current graph structure. Okay, so you see, we suppose we want to find top 4 neighbors. Okay, so we can find the top 4 neighbors here, then we build the connection, the edges between them. But sometimes the edges, we don't know the edges, the number of edges is too many. If the edges is too many, this means your search will take a longer time. So we will also apply some strategy to prune some unnecessary edges. Okay, we will talk it later. The second approach is the refinement approach to construct your graph. Okay, so you can see is steps how to do the refinement of your graph. So it's the first graph like this. So the first graph maybe is a random graph or use the KN graph. KN graph means I will connect, for each node, I will connect the top 10, top K neighbors, and I build the edges. So when you use this idea, you will see your initial graph is very dense. You see the edge connection. Okay, so it's a very dense graph. The dense graph is not very good because it means you will take a lot of time to traverse the graph. So the refinement step will try to reduce some edges. Also here you can see it's getting sparse. You can see every one step will get sparse. But sometimes you will also add some additional edges. So finally it's fine-tuned like this. So you will refine the graph by the pruning or the edges. And then finally you will generate it's not too dense, but also a little bit. It's also not too spicy. Okay, so we hope we can generate moderate sparse. So otherwise, the traverse of the graph will be very time consuming. And we also build some long edges in this step. So it means the shortcut. Okay, so any problem for the construction? Okay. And next, we talk about how to search in the graph structure. So now we have built this graph. Okay, and then given a query here. And here, okay, you see a bucket. This bucket is, we call it to store our candidates. When we visit this graph and to traverse the graph, we will visit several points and we will keep some of them. Here we keep the candidate size to be 3. It means we will keep at most 3 candidates in this bucket. Okay, so this is the basic structure we have to maintain, and also the graph structure. Alright, so give the query point here, the red point and the green point, and then we start to traverse the graph from the entry point here. It's called a N. Okay, we start from here. Okay, so first we will put N in our candidate bucket. Put here and compute the distance between N and your query. So the distance is 23. Okay, we also keep the distance to the query of this node. Okay, let's now start the first iteration. And at the start, now in our bucket we have a candidate here, so we check the best one. Now, currently there's only one. Okay, so this is also the best one. The best one node N here. Okay, we first check it. Check means we will verify its status. Check is the neighborhood. Okay, so it means checked in this candidate bucket. Okay, we label it as checked. Okay, with a yellow circle around surrounding it. And we explore its neighbors. So there are 3 neighbors associated with node N. Okay, then we compute the distance with the query and its neighbors. Okay, so you can see the distance to J, to distance to K, and to N. So the J, K, N are the neighbors you can explore from the node N, and we compute the distance J, K, N with the query, and here are the distance. Okay, so we put all the distance in our query, in our bucket, and the bucket is automatic search, automatic sorted. We sorted from the list from smallest to largest. Okay, with this sorting, and you can see, because we only keep at most 3 candidates, so this means there will be 1 have to be removed. So the next one N will be removed, and we only keep the J and K in our bucket. Okay, any problem? Okay, we remove it. And then is a second iteration. So the second iteration will start from your best one in your bucket. So now currently there are 3 candidates, but the best one is node J. Okay, so we check node J and explore its neighbors. So there are several neighbors, or so many. B, G, F, I, G, L, K. They are all the neighbors related to J. Okay, so we compute the distance. Note that node K is already visited before. So when we visit it, we also mark it. But here you don't highlight it in these slides. But if it's already visited, you don't need to compute the distance again. Okay, so K is already visited. Okay, so we can ignore it. and we only calculate the distance between for others at BF or so many points. Okay, so we collect these points from F, J, L, N, and sort it, put in, we already sorted it. We add 4 more nodes on it and sorted it in our bucket. But again, because the limitation of the bucket is 3, okay, so we only keep the top 3, B, G, I. They have the smallest distance, so we keep them, and then all the others will be removed. Okay, so we update our bucket, and now we move to here. Now in this bucket, the best one is node B. Now we move here. Okay, the path we check it, and we again find its neighbors. The neighbors including A, C, D. Okay, we compute the distance, and then sort again. Then remove the others. Okay, at the fourth iteration, you see the best one is C. It's the closest to the query, and then we check it and navigate. Check its neighbors. But most of the neighbors are already visited. Okay, so you can see the label is visited for A, G, and D. So I think E is not visited before. It's not visited, but it's an error in this slide. Okay, so actually you have to compute the distance between E and your query, but it also make an error on it. Okay, so but never mind, we will continue to the fifth iteration. Okay, and the fifth iterations, because you already checked C, D, B, you already checked C, and the next best is D. Okay, so you check the D here, and its neighbors. Some of them are already visited, and this one is a new one. So you compute the distance between H and your query, and put H on it. Okay, but this cannot be top 3, so it will be removed. Okay, so after the fifth iteration, the search can be stopped because all the candidates are visited. You can see in your bucket, all these are checked with a yellow circle. Okay, so they are all checked. Then we can start our search algorithm. Your final output will be your candidates. Here, we output the top 3 candidates, C, D, B, and also with their distance to the query. And the output 2 is the checked items. Okay, these are our checked items here, and also the path. So you find from N, J, B, C. Okay, this is your path. You explore, it's graph. And the output 3 is the visitor flag. Okay, there are several points are visited. Okay, so if there are neighbors, so these candidates you will explore many neighbors. Okay, they will be labeled as visited. Okay, any problem for the search? Okay, so I think it's very easy, very good examples to illustrate the idea. So Professor Matsui made a very easy understand slide to like an animation to illustrate the process of search. here are some observations. First, we consider the long time, the time complexity. Okay, the time complexity, for each item, if you compare their distance, their computation time is d, the dimensions, the number of dimensions. Okay, so the overall, the long time is actually how many times you compare with a node, and each node you take d complexity. And so the overall long time is the number of the items you compare when you traverse this graph. So it's approximate to the length of your search space and the average of our degree. So here is an example. So you start from here, and you only have one neighbor. Okay, your out degree is 1. And in the second stage, you have 2 neighbors. So your out degree is 2. And in the third, you also have 2 out degree. So in total, you have compared solar pace. You have solar space you visit. Actually, you have your length of your search space is 3, and each time the average out degree is like suppose it's 2. So the overall long time is just the length of your search space. Time is your average out degree. Okay, any problem? So in this case, we visit total 1, 2, 3, 4, 5. We visit 5 nodes. So the comparison we make is 5. And so the first observation is, if you want to speed up your search process, the first key point is try to shorten your search pace. To achieve this, you can make, when you construct your graph structure, you can try to add some long edges. We call this a shortcut. Or you use a hierarchical structure. It's part of the HMSW doing. You use a hierarchy to make your search to accelerate, to reduce your search pace. And also, maybe we can make the graph sparse. So because the over time is your length and the out degree. So the out degree, if you can reduce your out degree, it means you have less connection between these nodes, between your neighbors. So it's some part to also decrease your average out degree and reduce your search time. But the price is you will also decrease your accuracy. Okay, so the second point is if you want to make your graph to be sparse, you can delete some redundant edge. And the second observation is about the candidate size. So remember, in our search process, we keep a bucket. This bucket is you can set its size. If you set its size is 1, this means you only every time you just keep 1 candidate. We call such a strategy is a greedy search. Greedy search is a problem. So if you start from point node A and want to find your query, each time from A you will go to node B, and then at node B you will choose node C, right? Because you only keep 1 candidate, so you will not choose node D. But D has a beta edge to connect to E, which is the closest to the query. But if you only keep one candidate in your bucket, so you will drop node D and only keep C. And the C, at C you cannot further have a closer state to your query. So we call it like a local minimum, stuck in a local minimum. So it's a problem if you apply the query search. So the solution is you should perform a bin search. So in bin search, this means you will keep your candidate size to be greater than 1. So in our case, we can make the size to be 3. Okay, so from A to B, and B will find D and C, because you can put D and C in your bucket together. Okay, then D will find E, and this means you have several choices and to pick up the best one. Okay, so with bin search, you have more choices, so that you will not miss some better solutions. So the nodes are here. The larger candidate size you will have a better accuracy, but your result will be the search will be slower. Okay, so this is price. Okay, so in HNSW you can use the EF parameters to control what is the candidate size you want to keep. Okay, any problem? Okay, so remind you that in our term project we also use bin search to generate your candidate vector ID. So remember, so always if your accuracy is not very good, so maybe you can try to tune up your bin search size, try to improve its accuracy. Here are the pseudo codes from different papers. Okay, so you see all the papers, they have a different looks of their pseudo code, but the principles are the same. Let me show you some evidence. So here, this is a paper called ANNS. ANNS here, they say the candidates are stored in an array. And in the second paper, disk ANNS, they store their candidates in this line, in here. And the third paper, learning to route. Okay, this paper also have same code to store your candidate. But here they store their code in heap. Heap is a spatial structure, spatial structure that can automatically apply the search and the sorting on the elements. And also, if we want to remember in our search process, we have a check. Check is known. So the check code is here. Here, you see. And here is to label the code with visit. It's known that it's visited. It's also label it in this line and in this line. And here are the termination conditions. Here. So you can see the basic concept, the structure are similar. Okay, so later the authors will use the ANNS to reduce the idea. Okay, so let's take a break.